Hey everybody, it's Ripley again. We're going to explore a very special probability distribution. It's called the binomial probability distribution. And the best way to explain this is actually with a problem. And what we're going to do is we're going to set up something called the binomial setting. All right. Now your textbook doesn't refer to it as this. It just gives you rules of the binomial probability distribution. But we're going to call this the binomial setting. And I'm going to come up with a problem. All right. Let's say that worldwide, the probability of ordering a Big Mac, all right, the probability of a Big Mac being ordered by a car in a drive-thru is equal to 0.7. And we're doing a survey for whatever reason, maybe healthy eating or whatever. And we're going to watch the next 10 cars go through the drive-thru at a randomly chosen McDonald's. All right. So think about that. Now we're going to take n equals 10. That's our sample size. Okay. And what I want to know is what is the probability that exactly 5 of those cars, 5 of the cars order a Big Mac. That's what I'm trying to figure out here. Okay. Now, your spidey sense may be tingling here just a little bit. You may be saying, okay, Ripley, well, the probability of any car ordering a Big Mac is independent of any of the other cars ordering a Big Mac. So unless there's like this whole crew of 20 people that just got out of a football game and they're all, let's go get a Big Mac. Let's assume that that's not the case. All right. So you may think to yourself, okay, well, Ripley, why isn't it just 0.7 to the fifth? Or some of my more intrepid students might be saying, well, wait, don't we have to account for the students, or excuse me, for the cars that don't order a Big Mac? So why isn't it 0.7 to the fifth times 0.3 to the fifth? Remember, this 0.3 is the complement of ordering a Big Mac. Well, here's the problem. Let me show you this. You're on the right track. 5, 6, 7, 8, 9, and 10. Let's see, did I get a full 10 here? The problem with this probability right here, I'm going to change colors. The problem with this probability right here is there's this weird assumed order to it. So that really, what it's really doing is it's assuming that the first car orders a Big Mac, the second car orders a Big Mac, the third car orders a Big Mac, the fourth car orders a Big Mac, the fifth car orders a Big Mac, and then the rest of these guys don't order Big Macs. That's what it's really saying. But what we're looking for is exactly 5 of the cars ordering a Big Mac. So if you think about it, I'm just going to write under these spaces. If you think about it, let's say, change to black, let's say that the first car orders a Big Mac, but then we don't get another Big Mac until the 4th, the 5th, the 6th, and then the last car. And then the rest of these guys are misses. Well, what we have to account for is all of the ways in which that can happen. So I have to account for the first 5 cars ordering Big Mac and the last 5 not. The first one ordering the Big Mac, then the second one not, and then the next 4. The first car, then the second one, and then the first car ordering Big Mac, the second one ordering Big Mac, the third not, and then the 4th, 5th, and the 6th ordering Big Macs, and then the rest not. You see how complicated it can get. But the formula that I'm going to give you here in just a second is hopefully you'll see how that really accommodates for all of the possible combinations of cars going through the cars of size 10, going through the cars of size 10. Try that again. Of 10 cars going through the drive-through, and us picking up the total possible number of ways that exactly 5 Big Macs can be ordered, or exactly 5 of the cars can order Big Macs. Okay? But before we do that, let's create this here binomial setting that I'm talking about. It's actually pretty simple, and there's only there's only 4 different rules. Again, I've got construction going on underneath me, so if you hear any weird sounds, we'll blame it on the construction, regardless of whether or not it is. All right, the first is that there are a fixed number of trials. All right, that's the first rule of a binomial setting, fixed number of trials. So that's really your n size is fixed. It doesn't change. All right, step number 2 is independence. You have to have independence between trials. Independence between the trials. In other words, in this particular problem, the probability of any car ordering a Big Mac is not changed given another car ordering a Big Mac. Okay. Number 3 is that the probability cannot change. All right. So probability doesn't change. Whoops, doesn't change. All right. So in this case, it's always 0.7. Now you may say, really, that doesn't seem real practical. But again, let's say Big Mac did a little, or McDonald's did a little market research, and they figured out that it truly is the parameter, the proportion of vehicles that order a Big Mac is 70%. Excuse me. And lastly, but certainly not least, this is the most important thing and why it's called a binomial. Think binomial, binary. There are only two outcomes. Two outcomes. They either order a Big Mac or they don't. All right? They could order 17 Big Macs. They could order 93 Big Macs. But that just counts as a Big Mac. All right? So you take a car goes through the drive-thru. When they pull off, you ask them, hey, did you guys order any Big Macs? They either did or they didn't. There's no in between. Okay? All right. Now, the formula for this is actually very, very cool. And it's going to look scary. All right? But don't be afraid. But let's play for just a little bit. First things first, we're going to let n equal number of trials. I'm going to give you some notation here. I always hated the teacher. I didn't hate the teacher, but I always hated it when the teacher said, here's your formula, shut up, use it. Okay? We're going to let x equal the number of, and I'm going to use hits. And the reason that I use the word hits is because it can get really, really confusing if I let x equal the number of successes, which your book actually writes that. Most books actually do. But that can get really confusing if a quote-unquote success is actually a failure. And I'll show you what I mean. I'll twist this problem in just a second. Okay? Excuse me. So the n, now we're going to let p equals the probability of a hit, and q is equal 1 minus p, which is the probability of a not hit. Okay? Now, that's all you need. That's all you need to run a binomial probability problem. The formula is this. It's written this way. If I'm looking for the probability that x equals some number, which I'm going to let x equal, what's the easiest way to do this? I'm going to let it x equal big X. Okay, so this is a capital X. Okay? Excuse me. Here's the way that this is done. It's n choose x times the probability of a hit raised to the x times q raised to the n minus x. Now, those are all capital X's. In other words, there's supposed to be a little number here, but I'm running out of ways to write those things. And I'll show you when we do the example over here. Okay? So watch how this works. Let's go back. Let's define why we have what we have here. All right, so probably most of you are thinking, okay, this makes sense right here. This is the probability of a hit. This is the probability of a miss or a not hit. So those are accounted for. What is this n choose x thingy dingy? Well, hopefully you guys remember that n choose x is actually n factorial over n minus x factorial divided by x factorial times x factorial in the denominator, which is the number of ways to choose or not order x things from a total of n. Remember when I took 2 people to lunch from a total of 5? Well, let's take into account why that happens. Let's try and figure that out in the context of this problem. Again, the number of ways that I can choose 5 people that ordered Big Macs from a total of 10 is 10 choose 5. So the number of ways that I can pull, given 10 cars, the number of ways that exactly 5 of them can order Big Macs is 10 choose 5. And then this p to the x and q to the n minus x is the actual probabilities for each one of those possible combinations, and it's taken into account. Now let me show you how this is written up. Excuse me. So what this would be is the probability that x equaled 5. Okay? Now we take a deep breath, because this can get a little confusing because there's a boatload of numbers floating around at us. So I'm just going to follow my formula. Let's see. Before I get too crazy, let's go n equals 10. That's the number of cars. I know that p is 0.7. I know that q is 0.3. And I know that x equals 5. So we're finding the probability that x actually equals 5. All right? So here we go. I'm simply going to do 10, choose 5. Let's get out of our own way here. Times 0.7 raised to the 5th times 0.3 raised to the 5th. All right? Now, let's think about this. What is going to have the highest probability? In other words, the number of cars that's going to have the highest probability. Okay? Is it going to be that exactly 1 out of the 10 has that orders a Big Mac, that exactly 2 out of 10, that exactly 3, that exactly 10 out of 10? Well, hopefully you're thinking to yourself, well, wait a sec. Since the probability of getting any one car is getting a Big Mac is 0.7, then I'll bet you the highest probability, where are we, 7, 8, 9, 10, is going to be the probability that exactly 7 rather than exactly 5. So it would be the probability that exactly 7 cars. Well, we're going to play with that here in just a sec. But first, I'm going to throw this in my handy-dandy calculator. I'm going to show you guys how to do, excuse me, I'm going to show you guys how to do this, let's see, real quick on your calculators when we get back in class. So I need to go 10, and then I'm going to go math and prob, and I'm going to go NCR5, and then I'm going to go times 0.7 raised to the 5th times 0.3 raised to the 5th, and I get exactly well, not exactly, I have to round it, right? That's just silly, 0.103. So let's think about what that means, because we're starting to hopefully get savvy enough with all this crazy probabilistic stuff that we can start having real discussions about what this means. It means that if I were to watch 10 cars go through a McDonald's, and I were to repeat that experiment over and over and over again a large number of times, on average, the proportion of cars that would order exactly 5 Big Macs would be 0.103. Now, let's make sure I'm not lying. Let's do the probability that x equals 7. Now, the only thing that's changed here is that, I'm going to change the color of my pen. Excuse me. The only thing that's changed here is that instead of x equals 5, now we're talking about x equals 7. See, n is still 10. I got 10 cars. I have all those and all this. Okay, ready? So here we go. We're going to go 10, choose 7, times 0.7 to the 7th times 0.3 to the 3rd. It's kind of coinkadinkle that these two, see how this 3 and these 7s, I mean, I picked my numbers like that on purpose. Okay? And I'm going to throw it in my calculator real quick. All right. Second entry. Whoops. Sorry, you guys. Let's see. Second entry. And I'm going to do 10, choose 7, 0.7 to the 7th, and 0.3 to the 3rd. And I get that this probability is 0.267 approximately. That is the highest probability. And, excuse me, the cool thing is the numbers, we know that if this is the highest probability, that we know that the numbers will peter off from here. So the probability of x equaling 8 is going to be less than the probability of x equaling 7. Now, we haven't proven that yet, but that's our intuition. That's our sneaking suspicion. Now, let me show you what I meant by why I use hit and miss or hit and not hit rather than success and failure. Okay? Because a problem can be written as follows, and it can be really, really confusing. Whoops, don't do that. It can be really, really confusing. I'll show you what I mean. Excuse me. All right. So let's say that for any given cancer screening, the probability that I have cancer, all right, on a certain cancer screening particular to men, all right, a blood test, the probability that I have cancer is, let's say, 1% or 0.01. All right, so the probability of not, this little tilde means not, I'm going to interchange that with the bar, of not having cancer is equal to 0.99. Okay? Now, let's say that we take 100 men. So we got 100 men. Now, hopefully your brain's clicking. Oh, wait, 100 men. That's the number of trials. That's our sample size. So n equals 100. P equals 0.0. Whoa. Let's not write that up yet. Let's take our time and make sure we define this right. I want to find the probability that exactly 95, write this down, the probability that 95 men don't have cancer, or at least test positive for cancer, don't have cancer. All right? Now, so not having cancer is now considered a success if it were, right? Do you see what I'm saying? In other words, this is a hit, and this is a miss. Okay? Even though you may think that the probability of having cancer is going to be your P, and your probability of not having cancer is going to be your Q. It's all contextual. 95, I'm finding the probability that 95 men don't have cancer. So I know if n is 100, I know x equals 95. I know that P, which is my success, which means doesn't have cancer, which is a failure as far as testing for cancer is concerned, is 0.99. And I know that Q is 0.01. The moral of the story is take a deep breath and figure out exactly what a hit is. Don't figure out what a success or failure is, because you can get really screwed up with that. So let's just write it up, and then we can do it on our calculators when we get back to class. So the probability that x equals 95 is equal to 100, choose 95, times success is 0.99 raised to the 95th times 0.01, excuse me, raised to the 5th. All right, and then it becomes calculator problem. You can do it on your computer, you can do it on your calculator, you can do it all over the place. Okay, things like that. All right. So we now have the binomial probability formula. Life is good. Hopefully we've made a little sense of it. Okay?